Today, we're digging into something called SysML v2. And I know, that sounds a little technical, but stick with me, because this is about a whole new way we design and build pretty much everything in our world. This isn't just a minor update. It's like we're handing engineers a brand new language. So let's start with a really big question. How on earth do you build something like a self-driving car? A system so incredibly complicated that no single human being can actually hold the whole thing in their head at one time. How do you even begin?
Well, the honest answer is it's getting really, really hard. So hard, in fact, that the entire field of systems engineering is facing what they call a complexity crisis. And this isn't some theoretical problem for academics. It's a real-world, high-stakes issue that has massive implications for our safety.
So let's unpack that. What does this crisis actually look like on the ground? And why are the old ways of doing things suddenly becoming not just a little slow, but downright dangerous? Let's go back to that autonomous car. You're dealing with literally tens of thousands of individual safety requirements. You've got hundreds of tiny computers, controllers, all scattered through the vehicle, all trying to talk to each other in real time. On top of that, you have these incredibly complex algorithms trying to make split-second decisions in a chaotic world. It's too much. The sheer amount of information has gone way beyond what the human brain can reliably track. Now, the old solution, SysML version 1, tried to tackle this by letting engineers draw pictures, diagrams of how the system worked. But that created its own set of problems. Version 2 flips the whole script. It represents a huge mental shift. We're moving from drawing pictures to describing a system with the precision of computer code. And this right here, this says it all. This is the whole ballgame. We are leaving behind a world where the model is basically a collection of pretty but static drawings, and we're entering a world where the model is the data. It's alive, it's computable, just like the software that runs on your phone. You know, there's this quote from an engineer that just absolutely nails it. Under the old system, you spend so much time just trying to make the diagram look clean and organized that you could lose sight of the actual engineering details. The focus was on the picture, not the precision. So at its heart, SysML v1 was a graphical language that was borrowed from the world of software engineering. And because of that, and its total focus on diagrams, the models could end up being ambiguous. You know, two different engineers could look at the same drawing and walk away with two different interpretations. And in a safety-critical system, that's a recipe for disaster. Okay, so if that was a problem, what's the fix? Well, SysML v2 isn't just a patch. It's built on a completely new foundation that we can think of as three really powerful pillars. Those three pillars are KerML, which is the rock-solid foundation, the language itself, which is the blueprint the engineers actually write, and the API, which is the magic connection that lets the model talk to the rest of the world. Let's take a quick look at each one. First up is KML. And honestly, the best way to think about this is like the DNA of the language. It's all grounded in formal mathematics, which means every single statement can only have one possible meaning. It removes all the ambiguity, so a computer knows exactly what you mean every single time. Sitting on top of that logical foundation is the language itself. This is what engineers actually type out. It gives them the words to describe requirements, parts, and behaviors. And what's really cool is it uses this super consistent pattern. You define something once, like a blueprint for a sensor, and then you can reuse that blueprint hundreds of times throughout your model. And the third pillar, the API. This is a total game changer. Think of it as the nervous system of your project. It allows the model to send and receive data in real time with all the other tools engineers use. Simulators, requirements databases, you name it. It breaks down those frustrating data silos and creates one single living source of truth for the entire project. Okay, so now that we have this incredibly powerful new foundation, what can we actually do with it? Well, the first massive breakthrough is the ability to model a system in 4 dimensions, which allows us to write safety rules about time directly into the model. This is all possible because of a new concept called a 4D occurrence. The big idea here is that every single piece of the system, from a physical sensor to a packet of data, isn't just a static thing. It's modeled with a specific duration, a lifetime. It exists not just in space, but through time. And if you compare this to the old way, it's just night and day. In V1, time was basically just a note someone scribbled on a diagram. In V2, it's a core, computable property of the system. You can write explicit, testable rules about things like data freshness or latency, which for a self-driving car is absolutely everything. So what this really means is that a critical safety requirement, something like the data from the camera sensor must be processed in under 100 milliseconds, is no longer just text in a document that you hope someone tests. It is now actual, verifiable code inside the model that a computer can test automatically over and over again. Now, that powerful API we talked about, it finally delivers on a concept that engineers have been chasing for decades, the digital thread, a perfectly seamless flow of information across the entire life of a project. I mean, just picture this workflow. An engineer updates the specification for a sensor in the main model. A script that's watching the API instantly detects that change. It automatically kicks off a whole new set of simulations to test that change. And then it writes the pass/fail results right back into the model for everyone to see. It's fully automated, closed-loop verification. No emails, no meetings, it just happens. And this is where things start to feel like science fiction. Because SysML v2 is text, because it's code, it opens the door to a brand new era of collaboration between human engineers and artificial intelligence. This is the whole reason it works. A diagram is just a picture to a machine, but SysML v2 code has a clear, logical structure. It has meaning, and that means an AI can read it, understand the intent behind it, and even learn to write it. The possibilities this unlocks are just incredible. You could have an AI act as your junior architect. You give it a simple description in plain English, and it generates all the boilerplate model code for you. Or imagine an AI agent that is constantly monitoring your model 24/7, flagging potential errors, or even suggesting better, more efficient design choices in real time. It really all comes back to this one powerful idea. When you change the language you use to describe something, you fundamentally change the thing itself. By moving from the fuzzy language of drawing to the precise language of code, we are completely transforming how we design, build, and trust the systems that run our modern world. And that's the thought I want to leave you with. We've effectively turned the art of systems architecture into a programming language. So now that engineers can truly collaborate with AI on this level, what incredible, complex, and safer systems are we going to build next?